Hello everyone. In this video, I'll talk about the oscillator block of our microcontroller. I'll talk about each type of source you can use, how to configure them, and their differences, as well as some more information related to the oscillators. So, let's get started. When we say clock, we are referring to a signal that is turning on and off with a frequency, used to synchronize the operations of the microcontroller. It's impossible to explain why we need this clock signal or how it's used without going into silicon level logic, which could take a whole video series to properly explain. Instead, just know that we need this clock signal for the microcontroller to work properly, and each time the signal repeats, an operation will take place. So, to keep these operations properly synced up and going, we need to keep this signal switching with a constant known frequency. There are multiple ways to generate this signal, but the most practical way is to use the internal oscillator that exists in all but the very old microcontrollers. Most people, in most cases, will use the internal oscillator and be done with it. But there's a lot more to the oscillator module than you might think. So first, I'll talk about how to configure the internal oscillator without going into anything else. We can then skip the rest of the video and use the microcontroller like that. But I'll talk about everything else you can configure and show you how to use the external clock sources along with extra information later on in the video, which I suggest watching as well, but it's up to you. Before I teach anything, know that this microcontroller is rated for 64 MHz. You can easily find this information on the first page of any microcontroller. This means that you can run this microcontroller with a frequency lower than 64 MHz, but you can't run it any faster than that. You can technically overclock by externally feeding a higher frequency signal, but the amount of which you can overclock is based on luck, since the silicon on each microcontroller is different. But I don't recommend doing this. It will shorten its life, not to mention it's not guaranteed to work reliably. And reliability is one of the most important factors of a microcontroller since they manipulate circuitry. You may just cause short circuits by a random glitch, and you know how dangerous that can be. Now, take a look at this diagram. This diagram is very important, as without this, you'll be blindly trying to figure out what each register affects or which register does what through a mountain of text alone. This diagram will single-handedly make configuring of the oscillator module 10 times easier. And with this, you won't have to learn about the other parts of the modules if you don't want to use them. We'll keep referring to this diagram throughout the video. This end is your system, so whatever is outputted to here will be your system clock. Before we continue, don't forget that these registers are volatile, meaning they'll lose their configurations on reset, unless they are configuration bits like Fosc here. So the clock you're trying to mainly run off of will not necessarily be selected on reset. You'll need to configure them in runtime, which if you do wrong, may cause the microcontroller to not run at all. So, for example, if you don't choose internal oscillator here using these Fosc configuration bits, which as you know takes effect before runtime, and you don't have any external clock source connected, your microcontroller will not run, even if you try to configure SCS bits right here to run off of int_OSC in your main code. If you go to the register housing SCS bits, you'll see that the default state of these bits choose primary clock, which is determined by Fosc. To update the states of the SCS bits and to use int_OSC, the microcontroller has to run and execute commands, but since there is no clock source, it can't run, which means it can't change its clock source either, so it's just stuck there. This is why it's important to know the default states of some of the registers. There's one more thing. You'll see this PLL module in many PIC microcontrollers. It stands for phase locked loop. It's not easy to explain how it works, but all you need to know is that it multiplies the clock frequency by 4, meaning if you feed a 16 MHz clock signal to it, it will spill out a 64 MHz clock signal on its output. But be careful to read the datasheet. This PLL module is designed to work with input frequencies between 4 to 16 MHz, so you can't use it with any frequency you want. Now, say that you want to use the internal oscillator, which is this block. Let's see how we can read this diagram and configure everything you need. It seems that the internal oscillator has 3 blocks to generate different frequencies. Say you want to use the highest frequency, which is 64 MHz. You know that the base frequency you choose here can be multiplied by 4 by the PLL module. So we need 16 MHz from here, which happens to be the highest one, which is obviously deliberately designed. To get this 16 MHz on the output of the internal oscillator, we need to configure some bits, which the diagram is kindly showing us here. These 3 bit groups seem to control the divide circuit as well as the mux here, which is responsible for choosing which input gets to the output. Let's search these bit groups and find which registers they reside in so we can configure them, starting off with IRCF, which as you can see resides in the OSC con register. You can see that some of these bits have a dependency to the other 2 bits, which you can see from the fact that they connect to the same units to configure them. We'll get to them in a bit, But you can see here that only the options that have the value of 2 or less are dependent on the other 2 bits. What we want is 16 MHz, which is the value 7 right here, and this option is not dependent on the other 2 bits, so we don't have to worry about their values here. But for example, if you wanted to get 500 kHz clock signal, you could get it from either MF into SC or HF into SC, depending on the other 2 bits. Now let's search the second bit, which is MFI OSEL, which as you can see resides in the OSC-CON2 register. It's telling us that by changing this bit, we can derive these listed frequencies from either MF into SC or HF into SC. But we're not planning on using any of these frequencies, so it shouldn't matter what we choose here. Let's search the last bit, which is int SRC, which as you can see resides in the OSC tune register. It's telling us that by changing this bit, we can derive the 32 kHz frequency from either MF or HF into SC or LF into SC. But again, we're not planning on using 32 kHz, so it shouldn't matter what we choose here. To understand what these bits do and why changing them doesn't matter for 16 MHz that we want, you can look at this diagram instead, which shows you what's inside of the internal oscillator block. You can see from here that by choosing 16 MHz from IRCF, we are bypassing the other 2 bits, and that's why they don't matter. Now that we have into SC output at 16 MHz, we can either choose to directly run from it, or make it go through the FOSC configuration bits. But like I said before, on startup you have to go through the FOSC bits, since the STS bits are pointing to primary clock on reset. But after the microcontroller starts running, you can switch to directly using the into SC, even though you can do that by going this path, which I know seems weird. But it's designed this way so that if you're using an external clock, you can switch to the internal clock and vice versa in runtime. We want to use this PLL module here, so we're going to go this way. Now we have to configure FOSC configuration bits to output its into SC input. If you go to the register that houses the FOSC bits, you can see that we need to choose internal oscillator block here to do exactly that. I'll explain the other options later on in the video, but ignore them for now. You can also choose to output this clock onto the OSC2 pin, which I'll also talk about later on, so again, ignore it for now. After choosing the into SC as the output, we have the option to either select the clock directly at 16 MHz, or select the output from the PLL, which will be 4 times that clock frequency, meaning 64 MHz. We want the 64 MHz, so we need the PLL select here to be 0, is what you would think. But this diagram is actually wrong, and to get the PLL output, you want the PLL select to be 1, not 0, which is unfortunate since I told you that this diagram is very important, but what can you do? Now, before you try to find this PLL select bit, check these parentheses first. If we go to the nodes they're pointing at, we see another diagram. It seems that PLL select consists of multiple registers which were shrunk to fit the general diagram above. And this is where you can see why you want the output to be 1 and not 0. Activating PLL EN, which stands for PLL enable, should enable the PLL, which will make the output here 1, but the other diagram says to make it 0, so... Maybe this OR gate was supposed to be a NOR gate instead, or the MUX was supposed to have 1 on the top instead, like the ones here. Who knows? Just assume that you need to have 1 here to have the PLL output selected. You can also see the truth table for this combination of gates at the bottom here. Now, because the PLL EN is connected using an OR gate, turning this bit on will cause the PLL to always be selected, since the other input here doesn't matter and the output will be 1 no matter what. If you go to this bit and its explanation, you can see that it enables the PLL, but check the node it's pointing at. It's telling you that the PLL is active for all primary clock sources, which supports the behavior that this bit chooses PLL output no matter what. I know that the wording doesn't make sense here either. It seems the person who wrote this didn't really pay attention. I think the wording was supposed to be like this, but what can you do? Then why do we have this part, you might ask, for which I would answer, I don't know. It allows you to set this PLL CFG to have the PLL on at all times, so you can't configure it during runtime using this PLL EN bit. Or by clearing this PLL CFG, you can make the PLL configurable through software using the PLL EN bit. But all this only works if the microcontroller is not using the internal oscillator. This is a very niche occasion if you ask me, but whatever. We want the PLL on, so we can just ignore the rest and set the PLL EN bit in our code. Now we can configure STS bits to be 00, and we should have our 64 MHz clock transferred to the system. And like I said before, STS bits are 00 by default anyways, so you don't have to configure them. And after your code goes past these lines, you should have your microcontroller running at 64 MHz internal clock. And we're done. Now, I'll show you how to translate all of that in your code. I'll put the list of things we need to configure on the right again, as well as my microcontroller. First is the IRCF bit, which configures the internal oscillator block to output 16 MHz. Remember that it resides in the OSC con register. Next is FOSC, and you know that it's a configuration bit, so we can change it here in runtime. So let's go to the config.h file. Here's our FOSC bit, and we want it to be configured as the internal oscillator block, but it's configured as INT-IO67, which is internally defined by MPLAB. Is this the option we want? We can check the configuration bits to make sure. Here's FOSC, and if you open the settings tab for it, you can see that internal oscillator block is selected. And yes, that does correspond to INT-IO67, so we're good. Next up is PLLEN, which is a normal register, so let's go back to our main code. Remember that this bit resides in the OSC tune register. Now, after all of this code, your microcontroller should be running at 64 MHz. I'll copy-paste some code here from the first example project, but don't worry about it for now. It just configures the RD2 pin as output, and makes it turn on for 1 second, then turn off for 1 second on repeat. Also, you have to write this define statement to be able to use the delay functions, but don't worry about this either, as I'll talk about this and delays in the next video extensively. Let's program in C. If I put a timer next to the microcontroller, you can see that it's indeed turning on and off for 1 second each. Let's also talk about this PLLEN bit. Look at the PLLCFG config bit in the config.h file again. It's set, right? But if I go back to the main code and disable this PLLEN bit by commenting it out, you'll see that the microcontroller doesn't turn on and off for 1 second each anymore. Instead, it takes 4 seconds each, which means it's running 4 times slower, which also means the PLL is off. This is again happening because we're using internal oscillator, so the block above is 0 no matter what the PLLCFG bit is. So be careful, your microcontroller will only be at 64 MHz after this line of code, and before it, it will be 16 MHz instead. Also, your microcontroller will be 1 MHz in this part of the code, since the IRCF is also a normal register, and its default state selects 1 MHz. Now, this is the part of the video where I'll explain the other clock sources and the rest of the oscillator block. If you're content with just using the internal oscillator and don't care about any of that, you can stop watching here. But I suggest watching the rest anyway to learn more of your options as well as some extra information, but it's up to you. There are multiple clock sources you can use, and all modes usable by the microcontroller are listed in the FOSC configuration bits here. By the way, the term FOSC is commonly used to denote the main system clock frequency. Don't confuse it with this configuration bit, which is also named FOSC for some reason. When we talk about FOSC, that will usually refer to the main system clock frequency, and not this configuration bit. I mean, to begin with, FOSC stands for frequency of the oscillator. So with this configurations we've got here, FOSC would mean 64 MHz, since that is the frequency output to the system from our oscillator block here. Let's look at the oscillator block diagram again. These boxes with X denote a physical pin. So these boxes mean pin with OSC2 and pin with OSC1 functionality. This is the symbol for a crystal or a resonator, which we'll get to in a bit. So to use an external clock source, we'll be using these OSC2 and OSC1 pins, which are RA6 and RA7 pins respectively. Let's understand these two bits first, since they are very straightforward. PRI-CLK-EN is a configuration bit, and PRI-SD is a normal bit. Meaning you can't configure PRI-CLK-EN during runtime, but you can configure PRI-SD. They are OR together, and they both enable the primary oscillator block. So, you can set the PRI-CLK-EN bit and have the primary oscillator block active at all times, without the ability to turn it off during runtime. Or, clear the PRI-CLK-EN bit and have the option to turn the primary oscillator block on or off during runtime using the PRI-SD bit. Before we get into the external clock sources, here in the FOSC bits, you can also choose these options that allow you to output your clock on a pin as well. But be careful, the outputted clock will be your system clock divided by 4. This is because what you're outputting is your instruction clock and not the system clock. With PIC microcontrollers, you'll commonly see this FOSC divided by 4 terms in equations. This is because, as far as I know, most, if not all 8-bit PIC microcontrollers divide the system frequency by 4 to run its instructions. So the instructions take 4 system clock cycles to execute, but in return, the instructions can accomplish more in one instruction cycle. So don't take that as if the microcontroller is slowing itself down. the microcontroller is still using every system clock. You can see this in the instruction cycle section of the datasheet. Yes, every instruction takes 4 system clock cycles, but the instruction does 4 different micro instructions within that interval, so it's still using all the system clocks. You may ask, what's the point of doing this then? And the answer to that is a bit complicated, so I can't really go into details about it. Let's get back to our main topic. This is also why most peripherals of a PIC microcontroller will run off of system clock divided by 4. It's so the peripherals don't run faster than the instructions that are reading or configuring them. Also, in case you didn't realize, the output is system clock divided by 4, right? But remember that PLL module can multiply the clock by 4 as well. So if you use this clock to run another microcontroller, you can still synchronize them and use them with the same frequency using PLL. Neat, right? One more thing. You can see here that only some options allow for the clock to be outputted. This is because the clock is outputted on OSC 2-pin. It says RA6 here, but that is also OSC 2-pin. This is because some of the modes require both OSC 1 and OSC 2 pins to be used, and some only require the OSC 1 pin. We'll get to them in a bit, but if the mode requires both pins like these ones, you can't get an output clock from them. Let's start with the most common external oscillator options, which are these LP, XT, and HS modes. These modes are for when you're using those crystals or ceramic resonators. Normally, you need driver circuits to generate clock signals from these components, but that circuit is already implemented for you inside of the microcontroller. You just need to connect the component between the OSC1 and OSC2 pins. But be careful, you will also need these 2 capacitors even though they don't show up on some of the schematics. These are called load capacitors, and without them, the oscillator won't work. The capacitance value depends on the oscillator component, as well as the stray capacitances caused by the environment such as breadboard, and that's also why they're not included in the driver circuit. Also, both capacitors have to be identical. Generally, ceramic 22 picofarad caps will be recommended, and will work in most cases. I'll put a link down below for how to calculate this if you're interested, but you will need to find the datasheet of your oscillator. Also take care that these series and parallel resistors may be required. This goes into more advanced problems that will most likely require an oscilloscope to figure out. Luckily, most of the time you won't need these resistors anyways, but it is still something to look out for. You may have the question, why use an external oscillator, especially when you can save cost and space by not having these extra components. The answer to that can be many things, but the most common reason would be the accuracy. Internal oscillators are done using RC circuits, since putting a crystal inside of your microcontroller is not an option, given its size and fabrication difficulties. And unfortunately, RC circuits are not that accurate. If you go to the first page of your datasheet, most of the time you'll find the internal oscillator calibration value here. This 1% error is good enough for most applications, but there are cases when you need better, like high-speed communications or real-time clocks and etc. That is the main reason to use external oscillators, since even the cheap ones will always be more accurate, and you can always spend extra to get even more accurate ones. Not to mention, external oscillators can generally reach higher frequencies than the RC circuits can, but let's leave it at that. Now, as for which option to select, each option changes the gain of the driver circuitry inside of the microcontroller, so pick the correct one according to your oscillator. Also, the higher the gain is, the more the current consumption by the circuit will be, which also means more power usage. From the lowest to the highest gain by order is LP, XP, HS with MP, and HS with HP. Now, for LP and XT modes, there are no recommended clock limits on the datasheet as far as I know, but another microchip source recommends that LP mode is used with frequencies lower than 200 kHz, and XT mode is used with frequencies lower than 4 MHz. As for HS mode, there are 2 sub-modes that you can use it with. These are called MP for medium power and HP for high power. Medium power is recommended for frequencies between 4 to 16 MHz, and high power is recommended for frequencies above 16 MHz. But remember that 64 MHz is the highest frequency recommended for this microcontroller. Also, these crystals or resonators require 2 pins, so you can't have a direct output for your clock on the OSC2 pin, like some of the other options. The EC modes you see here are used when you have a direct logic level clock source, meaning the source is not an oscillator or a resonator, but instead it is a direct clock signal. Since the source is a direct clock signal, you don't need 2 inputs like you did with the crystal oscillators, so if you choose these options, your OSC2 pin can be used as a digital I/O, or if you want, you can choose these options to output your system clock divided by 4 on it as well. You can choose from 3 different power modes. If your clock source is less than 500 kHz, choose one of these. If it's between 500 kHz and 16 MHz, choose one of these. and for frequencies higher than 16 MHz, choose one of these. Next one is a niche option, but you can use an RC circuit as a clock source, like this. This is the diagram for RC drive circuit. The microcontroller has a Schmitt trigger and a MOSFET inside when using this mode. So all you need to do is connect a resistor and a capacitor like shown on the screen. From here, you can see that the resistor will slowly charge the capacitor to the VDD level. When the voltage reaches the on voltage of the Schmitt trigger, the output will go high, which will produce a clock signal. But the N-channel MOSFET is also connected to this output, which will turn on and pull the capacitor to the ground, discharging it. This will cause the Schmitt trigger output to turn off, which will also turn off the MOSFET. Now the capacitor will start to charge again, completing the loop to constantly generate the clock signal. Now, you can't exactly calculate the frequency generated by this circuit. You can make estimations through the values of the components and the VDD voltage, but the tolerances of the components, the temperature, the noise, and way more will cause this value to drift, potentially drastically. So the use of this feature is very niche, but if you need it, you'll know. This also allows the resistor to be replaced by a potentiometer to alter the frequency on the go, but the non-exact frequency means you won't be able to use the delay functions or the timers properly, so it's a very specific option. Also, be careful that there are minimum and maximum values recommended for the resistor and capacitor to avoid problems with noise. And because this circuit also needs only one pin to operate, you can choose this option to have the system clock divided by 4 outputted on OSC 2 pin. And that covers all clock sources. But there's still one more thing to tackle, which is the secondary oscillator block. This oscillator circuit is designed to be used with a 32 kHz oscillator, so you can't use it any other way, and you still need the 2 load capacitors to run this circuit properly. This circuit is mainly used to directly feed clock to the timers, but I won't go any deeper into that. I'll talk about this more when I make a video about how to implement a real-time clock inside the microcontroller. Also, this secondary oscillator can be activated independently, since it doesn't share the pins or the circuitry of the primary clock module. That's it with the oscillator block, and in the next video, I'll talk about delays, which is kind of a second part to this video, since it's also about oscillators in a way. But this video is getting a little too long for them to be mentioned here. And that's the end of the video, and thank you for watching. If you liked the video, you can always leave a like and subscribe, it's always appreciated, and I'll see you in the next video.